All right, so let me start again by reminding you what it is that was done last time. So if you say, can you summarize for me in a few words main ideas? So I would like to do that. So what I did last time was to show you how to handle motion in more than one dimension, and I picked for it 2 dimensions as the standard way to explain it. Okay, by the way, I would like to make one recommendation. If you guys are coming in a little late, don't worry about submitting the homework. Just come in and settle down, because it's very hard to lecture with this amount of traffic. I do try to start a few minutes late, but I also have to finish a few minutes early so you can go to your next class. And also, people who come in early, maybe you should try to sit in the middle part of the classroom so the latecomers can come in without too much disruption. All right, so summary of last time. If you live in 2 dimensions or more, you got to use vectors to describe most things. So the vector was, typical vector is called V or A or B, something with an arrow on it. Most important vector is position vector that tells you where the object is. It's got components which are x and y that could vary with time. I and j are unit vectors in the x and y directions. And you can deal with the vector in one of 2 ways. You can either think of it as an arrow and imagine the arrow, or you can reduce it to a pair of numbers, x and y. If you want to add 2 vectors, you can add the arrows by the rule I gave you, or just add the components of x of the 2 guys to get the component of the sum, and likewise for the y. I mentioned something of importance, of increasing importance, only later, which is that you are free to pick another set of axes, not in the traditional x and y direction, but at some oblique direction. If you do, the unit vectors are called I prime and j prime. The components of the vector change. You can imagine that if a vector is viewed from an angle, then its components will vary with the perspective. So the components of the vector are not invariant characterizations of the vector. Whereas the vector itself has a life of its own, the components come in the minute you pick your axes. So it's not enough to say these are the components of the vector. You got to tell me I'm working with I and j, which are defined in the following manner. I gave you a law of transformation of the components, namely if the vector has components ax and ay in one reference frame and ax prime and ay prime in another reference frame, how are the 2 related? They come from writing I prime and j prime in terms of I and j, then sticking it into the expression and identifying the new representation. Somehow, when I told you to invert the transformation, some of you had some difficulty. Maybe you didn't realize that they are just simultaneous equations that you solve. Normally, if I tell you 3x plus 4y is 6 and 9x plus 6y is 14, you know how to solve it. It's like really the same kind of problem, except that the 3 and 4 were all replaced by sine phi and cosine phi, but they're just some numbers, and you eliminate them the same way you eliminate them. But I've given you a homework problem where you can try your skills. So when you go today and look at the homework, you'll find, besides problems from the textbook, one extra problem that deals with all of this. Then I gave you one other very important example of a particle moving in the xy plane. X and y can be whatever you like, but I picked a very special example where it looked like this. R times cosine omega t is times I plus r times sine omega t. Now you should go back and remember what we did. If it took you a while to digest it, I asked you to think harder. This describes a particle that's going around in a circle. We know it's going around in a circle because if I find the length of this vector, which is the x squared part plus the y squared part, I just get r squared at all times, because sine squared plus cosine squared is 1. So we know it's moving on a circle of radius r. Furthermore, as time increases, the angle omega t is increasing in this fashion. And omega is called the angular velocity. And I related it to the time period, which is the time it takes to go around a full circle, by saying once you've done a full circle, omega t better be 2 pi. So this new quantity omega, which may be new to you, is related to the time period for which you have an intuitive feeling. How long does it take to go one round in this fashion? You're also free to write it in terms of the frequency. The time period and frequency are reciprocals. If it takes you 1/60th of a second to go around once, then you do it 60 times a second. So omega is really very simple quantity. It's related to the frequency with which you go around the circle, but it's multiplied by 2 pi. Why is that? Frequency is how many times you go around, and 2 pi is the rate at which the angle is being changed. But if every revolution is worth 2 pi radians, then 2 pi f is the number of radians per second. So f is revolutions per second, and 2 pi f is radians per second. And it's called the angular velocity. The most important result from last time was that if you took this r and you took two derivatives of this to find the acceleration, d2r over dt squared, try to do this in your head. If you took the two derivatives of this guy, first time it will become minus omega sine omega t. Second time it will become minus omega squared cos omega t. In other words, it will become minus omega squared times itself. Same thing here. And the final result is the acceleration is minus omega squared times the position. That means the acceleration is pointing towards the center of the circle, and it has a magnitude a. When I draw something without an arrow, I'm talking about the magnitude. It is just omega squared r. But I had shown you yesterday that the velocity, and I'm sorry, the speed of the particle as it goes around the circle is this. Again, you should make sure you know how to derive this. You can do it any way you like. You can take one full circle, you realize the distance traveled is 2 pi r, divide by the time, and you will get this. Another way, take the derivative of this, get the velocity vector, and you notice its magnitude is a constant, and the constant will be omega r. So whichever way you do it, you can then rewrite this as v squared over r. This is called the centripetal acceleration. This is the acceleration directed toward the center, and I told you this is a very important result. You got to get this in your head. Whenever you see a particle moving in a circle, even if it's at constant speed, it has an acceleration, v squared over r, directed towards the center. This formula doesn't tell you which way it's pointing because it's a scalar, it's not a vector equation. If you want to write it as a vector equation, you want to write it as v squared over r minus I want to say that it's pointing in the direction toward the center. So sometimes what we do is we introduce a little vector here called E sub r. I'll tell you more about it later. E sub r is a vector at each point of length 1 pointing radially away from the center. It's like the unit vector I. Unit vector I points away from the origin in the x direction. J points away from the origin in the y direction. ER is not a fixed vector. At each point, ER is a different vector pointing in the radial direction of length 1. The advantage of introducing that guy is that if you like, I can now write an equation for the acceleration as a vector. The magnitude is v squared over r. The direction is negative ER. So ER, E sub r, is a new entity I've introduced for convenience. It plays a big role in gravitation, in the Coulomb interaction. Good to have a vector pointing in the radial direction of length 1. So that's what it is. That's really the heart of what I did last time. Then we did some projectile problems. You shoot something, you should know when it will land, where it will land, with what speed it will land, how high it will go. I assume that those problems are not that difficult, and I've given you a lot of practice. So now I'm going to move to the really important and central topic. I guess you can guess what that is, right? We're going to talk about Newton's laws. This is a big day in your life, okay? Because this is when you learned the laws in terms of which you can understand and explain a large number of phenomena. In fact, till we do electricity and magnetism the next semester, everything is going to be based on just the laws of Newton. It's really amazing that somebody could condense that much of information into a few, namely 3 different laws. That's what we're going to talk about. So let's start. So now, your reaction may be that you've seen Newton's laws, you've applied them in school. I got to tell you that I realized fairly late in life they're more subtle than I imagined the first time. It's one thing to plug in all the numbers and say, I know the Newton's laws and I know how they work. But as you get older and you have a lot of spare time, you think about what you're doing, which is something I have the luxury of doing right now, and I realize this is more tricky. I want to share some of that with you so you can fast forward and get the understanding. Took me much longer to get. That's what I'm going to emphasize more than just plugging in the numbers. Of course, we have to also know how to plug in the numbers so we can pass all the tests, but it's good to understand the nature of the edifice that was set up by Newton. So first statement by Newton, I don't feel like writing it down. It's too long, and everybody knows what the law is. It's called the law of inertia. So let me just say it and talk about it. Law of inertia says that if a body has no forces acting on it, then it will remain at rest if it was at rest to begin with, or if it had a velocity to begin with, it will maintain that velocity. So one way to say it is every body will continue to remain in a state of rest or uniform motion in a straight line. That's another way of saying maintain a velocity if it's not acted upon by a force. Now, what makes the law surprising is that if I only gave you half the law, namely every body will remain at rest if it's not acted upon by a force, you will say that's fine. I accept that because here's something, you leave it there, it doesn't move, it's not a big surprise. People were used to that from the time of Aristotle. But Aristotle used to think that if you want something to move, there has to be some agency making it move. That agency you could call force. The great discovery that Galileo and Newton made is that you don't need a force for a body to move at constant velocity. That it's very clear you don't need a force if something is doing nothing, just sitting there. The fact that you don't need a force for it to move forever at a given speed in a given direction, that's not obvious because in daily life you don't see that. In daily life, everything seems to come to rest unless you push it or you pull it or you exert some kind of force. But we all know that the reason things come to a halt when you push them is that eventually some friction or drag or something is bringing them to rest. And somehow, if you could manufacture a really smooth, frictionless surface, that if you took a hockey puck or something in an air cushion and you give it a push, in some idealized world, it'll travel forever. So it's hard to realize that in the terrestrial situation, but Galileo already managed to find examples where things would roll on for a very, very long time. But nowadays, if you go to outer space, you can check for yourself that if you throw something out, it just goes on forever without your intervention. That it's in the nature of things to go at a constant velocity. They don't need your help to do that. Now, you have to be careful that this first law of Newton is not valid for everybody. In fact, I'll give you an example in your own life where you will find that this law doesn't work. So here's the situation. You go on an airplane, and then after the usual delays, the plane begins to accelerate down the runway. At that instant, if you leave anything on the floor, you know it's no longer yours. It's going to slide down, and the guy in the last row is going to collect everything, right? Why is that? Because we find in that plane, when objects are left at what we think is at rest, with no external agency acting on them, they all slide backwards towards the rear end of the plane. That happens during takeoff. That doesn't happen in flight, but it happens during takeoff. So that is an example of a person for whom the law of inertia does not work. So this is something you guys may not have realized. Newton's laws are not for everybody. You have to be what's called an inertial observer. If you're an inertial observer, then in your system of reference, objects left at rest will remain at rest. The plane that's ready to take off or is taking off is not such a system. The Earth seems to be a pretty good inertial system because on the ground, You leave something, it stays there. It depends on what you leave. If you leave your iPod, it's not going to stay there for very long. But then you can trace it to some external forces which are carrying your iPod. But if you don't do anything, things stay. So here is the main point. The point of Newton is two things in the law of inertia, which one may think is trivial. First, free velocity, constant velocity, can be obtained for free without doing anything. And there are people for whom this is true. For example, in outer space, if you're an astronaut, you send something, you'll find it goes on forever. Here's another thing. If you find one inertial observer, namely one person for whom this law of inertia works, I can manufacture for you an infinite number of other people for whom this is true. Who are these other people? Do you know what I'm talking about? If I give you one observer for whom the law of inertia is true, I say there are others for whom it's also true. Yes? Did you hear that? Let me repeat that. First of all, if the law of inertia is valid for me, it's valid for other people in the same room at rest with respect to me. Because if I think it's not moving, you'll think it's not moving. That's just fine. But suppose you are in a train and you're moving past me and you look at this piece of chalk. Of course, everything in my room is going backwards for you. But things which are at rest will move at a constant velocity opposite to the velocity that you have relative to me. So you will find that objects which had a constant initial velocity maintain the velocity. So if I am an inertial observer, another person moving relative to me at constant velocity will also be an inertial observer. Why? Because any velocity I ascribe to a party, to a particle or an object, you will add a certain constant to it by the law of composition of velocities, right? All velocities I see, you will add a certain number to get the velocities according to you. But adding a constant velocity to objects does not change the fact that those which were maintaining constant velocity still maintain a constant velocity. It's a different constant velocity. In particular, things that I say are at rest, you will say are moving backwards at the velocity that you had relative to me. Things that I say are going at 50 miles per hour, you may say are going at 80. But 50 is a constant and 80 is a constant. Therefore, it's not that there's only one fortunate family of inertial observers. There's an infinite number of them, but they're all moving relative to each other at constant velocity. So if the Earth is an inertial frame of reference, if you go in a train relative to the Earth at constant velocity, you're also inertial. But if you go in a plane which is accelerating, you're no longer inertial. That's the main point. But the point is there are inertial frames of reference. Now you must know the Earth is not precisely inertial because the Earth has an acceleration. So maybe, can you tell me why I'm sure the Earth has an acceleration? Yes? It's going around the sun. Let's imagine it's a circular orbit. Then we've just shown here it's an accelerated frame of reference. It just turns out that if you put the v squared and you put the r, r is 93 million miles, you will find that acceleration is small enough for us to ignore. But there are effects of the Earth's acceleration which will demonstrate. The Foucault pendulum is one example where you can see that the Earth is rotating around its own axis. Then the fact that Earth is going around the sun, all of them mean it's really not inertial, but it's approximately inertial. But if you go to outer space nowadays, you can find truly inertial frames of reference. Okay, so that's the first law. First law, if you want to say, okay, what's a summary of all of this? Summary is that constant velocity doesn't require anything. Now, the reason things don't have it looks like a tautology because you look around, nothing seems to have its velocity forever. Then you say, oh, that's because there's a force acting on it. It looks like a tautology because you are never able to show me something that moves forever at constant velocity, because every time you don't find such a thing, I give an excuse, namely a force is acting. But it's not a big con, because you can set up experiments in free space far from everything where objects will in fact maintain their velocity forever. That's a possibility. And it's a useful concept on the Earth because Earth is approximately inertial. Okay, now you come to the second law, of course, which is the law. This is the law that we all memorize and learn. And it says that if a body has an acceleration, then you need a force, and the relation of the force to acceleration is this thing. Now, I have to say a few words about units. Acceleration is measured in meters per second square. Mass is measured in kilograms. So the way to measure force is in kilogram meters per second square, but we get tired of saying that long expression, so we're going to call that a Newton, right? Okay, if you'd invented it, we'd call it whatever your name is, but this is the guy who invented it, so it's called a Newton, usually denoted by capital N. So typical problem that you may have done, in your first pass at Newton's law, someone tells you a force of 36 newtons is acting on a mass of whatever, 4 kilograms, what's the acceleration? You divide and you find it's 9, and you say, okay, I know what to do with Newton's laws. That's where I want to tell you that it's actually more complicated than that. Let's really look at this equation. Take yourself back to 1600, whatever, whenever Newton was inventing these laws. So you don't know any of these laws. You have an intuitive definition of force. You sort of know what force is, right? Somebody pushes you or pulls you, that's a force. And suddenly, you are told, here is a law. Are you better off in any way? Can you do anything with this law is what I'm asking you. What can you do with this law? So I give you Newton's law and say, good luck. What will you do? What does it help you predict? You can even tell if it's true. Here's a body that's moving, right? I want you to tell me, is Newton right? How are you going to check that? Well, you want to measure the left-hand side and you want to measure the right-hand side. If they're equal, maybe you will say the law is working. So what can you measure in this equation? Pardon me? All right. So let's start with acceleration. What's your plan for measuring acceleration if some little thing is moving? How do you plan? What do you need to measure it? Right, but what instruments will you need to measure it? You are supposed to really measure it. So what will you ask me for? A watch, yes. And what else? A ruler. Okay. Or that's right. I mean, you don't mean Queen Elizabeth, right? You mean some long. Very good. Okay, so what you really want, a ruler may not be enough, but maybe it's enough. So here's a long ruler, and here's this thing moving, right? And you ask for a Rolex, so here's your watch. It's telling time. Tell me exactly what you want to do to measure acceleration. What do you have to do? I want the acceleration now. What will you measure? Okay, you go ahead. Okay, you can try. It may not be at rest to begin with. It's doing its thing. It's going at some speed. Yes?
Measure the distance it travels over a constant interval of time.
That'll give you the velocity.
Well, if you do like distance after 1 second versus distance over the next second versus distance over the third second, you can see how it increases.
Good. So in principle, let me repeat what he said. He said, first let it go a little distance. Take the distance over time. That gives you the velocity now. Let it go a little more. That gives you the velocity later. Take the difference of the two velocities, divide by the difference of the two times, and you got the acceleration. Of course, you have allowed it to move a finite distance and a finite time. So what you should imagine doing is making these 3 measurements more and more quickly, right? You need 3 position measurements. Now, a little later, and a little later, because between the first and second you get a velocity, second and third you get another velocity. Their difference divided by the difference in times is going to be the acceleration. But if you imagine making these measurements more and more quickly, in the end, you can measure what you can say is the acceleration now. That's the meaning of the limit in calculus. You take delta x and you take delta t. What's the meaning of delta x and delta t going to 0? It means measure them as quickly as you can. So in real world, no one's going to measure it instantaneously, but we can make the difference as small as we like. Mathematically, we can make it 0. So in that limit, we can measure velocity right now. That means we can also measure velocity slightly later and make the slightly later come as close to right now as we want, and then that ratio will give you acceleration. So acceleration is the easiest thing to measure of these three quantities. We all have a good intuitive feeling for what acceleration is. So you want to test if what Newton told you is right. You see an object in motion, you find a, and you given a certain numerical value, 10 meters per second squared. But that's not yet testing the equation because you got to find both sides. So what about the mass? What's the mass of this object? Anybody want to try from this section here? Yes?
You could use some sort of a standard unit of mass and then a balance to measure the mass of something else, like put it at a certain distance from on a scale and figure out the relative mass.
Okay. His idea was following. You take a standard mass and you maybe go to a seesaw, right? You put the standard mass here and you put some other fellow, the mass you're looking at there, and you adjust the lengths, and when it balances, you can sort of tell what this mass is, right? But suppose you were in outer space. There's no gravity. Then the seesaw will balance even if you put a potato on one side and an elephant on the other side. You cannot tell the mass. Because what you are doing now is appealing to the notion of mass as something that's related to the pull of the earth on the object. But Newton's laws, you see, you got to go back and wipe out everything you know. If this is what you have, there is no mention of the earth in these equations. And yet the notion of mass is defined. So it's not talking about the gravitational pull of the earth on an object. Yes?
Well, if you had an object that you say has a certain mass that you don't know, and then you took one that's the same density but say twice the size, and you can see if it's twice the force.
But do you know what the force on the body is? We don't have to measure that either. Do you agree? We don't know what the force is because we are hoping to say force is going to be m times a. We're just getting around to measuring m. So it looks like a circular definition right now. Yes?
If you knew what material this object was made of and its density, and you knew the size, then you could find out.
But density is mass over volume. But we don't know the mass. Right?
But if you knew the density of that,
How is anyone going to give you the density of anything? We're just asking what's the mass of any object. We have not yet found a satisfactory answer to what's the mass of an object. Yes?
are we still operating in outer space?
Yes. This cannot depend on the planet Earth.
Could we have, by any chance, a spring?
Yes?
Whose spring constant in the definition?
I'm sorry. What did you just say? You can have a spring.
Yeah, you could have a spring, and you can compare how fast different objects will travel when the spring is compressed and they're placed against it and released, but you don't make comparison.
Okay. Let me repeat what he said. He said, take a spring to outer space and hook up some objects to them and see how fast they move and do a comparison. That's fairly close to what I had in mind, but it's not the word perfect answer. And I just want to take some time thinking about it. Yes? What do I learn from the period? How? Remember, you cannot peek into chapters 6 and 7 because you've seen it before. I'm asking you if somebody wrote apparently Shakespeare's plays for him. That's one of the rumors, right? Suppose Newton comes to you and says, I have this great law, but I don't want to publish it under my name. So I'm going to give it to you. And you have got this new law, but how are you going to sell this, right? You got to tell people how to use it. And you realize it's very subtle because the very first thing in that equation, which is m, is not yet being defined. And he gave an answer which is fairly close. It doesn't rely on gravity, doesn't rely on the planet. Now, you cannot say to me, take a force due to a spring and see what force it applies and divide by the acceleration and get the mass, because we haven't defined force either. You got to realize that. Let me ask you something. How do we decide how long a meter is? Can you tell me how do we know how long a meter is?
It's just sort of arbitrary.
Right.
Pick an arbitrary mass as well, like one object, which is our arbitrary mass.
And we will call it. First thing you got to do is that some of these things are not God-given. A meter, for example, is not deduced from anything. Napoleon or somebody said the size of my ego is 1 meter. That's it. That's the new unit of length. You take a material like silver, you put it in a glass case, and that's a meter, and that's the definition of a meter. That's not right or wrong. Then I ask you, what is 2 meters and what is 3 meters? We have ways of doing that, right? Take the meter and put it next to the meter. That's 2 meters, or cut it in half, or use some protractors and dividers and compasses. You can split the meter into any fraction you like. Likewise, for mass, we will take a chunk of some material and we will call it a kilogram. So I should give you some hint. So that kilogram, I don't expect you to deduce. That is a matter of convention. Just like 1 second is some convention we use, and 1 meter is some convention we use. So I'm going to give you a little help. I'm going to give you a glass case, and in the glass case is an entity which is 1 kilogram by definition. Yes, then I give you another object, elephant. Here's elephant, and I'm telling you what's the mass of the elephant. How do you find its mass? You got to take the hint he gave. I give you a spring and an elephant. What should we do? Yes?
Measure how far, if you hung the elephant from the spring.
No. Remember, when we hang the elephant in outer space, nothing's going to happen.
Oh, okay.
Right.
Measure how, okay, so you push the elephant, and you measure how far, what the distance from the unstretched spring is that the elephant travels in either direction.
Okay.
And then you also do that with the 1 kilogram, and it should be proportional to how far from the resting state of the spring. That should be the proportion that the 1 kilogram object is to the elephant.
When you say push the elephant, you want to push it in a particular way? Or what do you want to do?
Or towards the, to compress the spring or to.
That is correct, but you don't want to give it a definite push. Yes?
You push it radially along the axis of the spring because we know that the centripetal force is mv squared over t.
Yeah. Or maybe, yeah, maybe that's an interesting thing, but that's correct. You can do that too, but let me now put you out of your suspense. I think I've heard bits and pieces of the answer everywhere, so I don't want to wait till we get it word perfect. The point is, the 1 kilogram is a matter of convention. So we want to know what is the mass of the elephant. So we can do the seesaw experiment you suggested, but the seesaw experiment requires gravity, so we don't want to do that. So a spring will, on the other hand, exert a force. We don't know what the force of a spring is. If you assume that, you're not playing by the rule, because we don't know what force it exerts. But we do know it exerts a force. So here's what you do. You hook one end of the spring to a wall, and you pull it from rest by some amount, and you attach the 1 kilogram mass to it. Yes?
One problem that we have, though, is if we're in outer space, where are we going to find a wall that won't move?
A wall that will not move?
No, actually, if you hook it up to any wall in outer space, what does it do?
Well,
Now I'm cheating. And
no, you're right. What can actually happen is that if you're in an enormous laboratory, which is made up of an enormous object, then you will find that you can, in fact, attach it to the wall. You can go to outer space. No, it won't move very much. And we can, once we know enough dynamics, we can answer your question. Does outer space even rob you of something to which you can anchor a spring? Answer is no. You can anchor things to objects in outer space. They just won't act the way gravity does, but you can nail it to the wall and pull one end. So you pull one end. We don't know what force it exerts, okay? But it exerts some force. Now I tie this 1 kilogram mass to it. I let it go, and I find the acceleration. That is the force which I do not know in magnitude, okay? But this is the acceleration of the 1 kilogram mass. Then I bring the elephant, and I pull the spring by the same amount, and I find the acceleration of the elephant. And the denominator is obviously the mass of the elephant. The force is not known, but it's the same force. So when I divide these two numbers, I'm going to find A1 over AE is equal to ME over M, which is the 1 kilogram mass. So what we needed was some mechanism of exerting some fixed force. We didn't have to know its magnitude. But the acceleration it produces on the elephant and on the mass are in the inverse ratio of their masses. So if you knew this was 1 kilogram, then the acceleration of the elephant, which will be some tiny number, maybe 1/100th of what this guy did, the mass of the elephant is then 100 kilograms. Now, there are again subtleties even here. If you think harder, you can get worried about other things. For example, how do I know that when I pull the spring the first time for the mass, it exerted the same force when I pulled the spring the second time for the elephant? After all, springs wear out. That's why you change your shock absorbers in your car. After a while, they don't do the same thing. So first, we got to make sure the spring exerts a fixed force every time. Now, you can say, how am I going to check that? I don't have the definition of force yet, but we do know the following. If I pull the 1 kilogram mass and I let it go, it does something, some acceleration. Then I pull it again by the same amount and let it go. I do it 10 times. If every time I get the same acceleration, I'm convinced this is a reliable spring that is somehow producing the same force under the same condition. On the 11th time, I pull the mass out and put the elephant in. I have some degree of confidence I'm working with a reliable spring, and then I will get the mass of the elephant. Why is it so important? It's important for you guys to know that everything you write down on the notebook or blackboard as a symbol is actually a measured quantity. And you should know at all times how you will measure anything. Because if you don't know how to measure anything, you are doing algebra or trigonometry, you are not doing physics. So this also tells you that the mass of an object has nothing to do with gravitation. Mass of an object is how much it hates to accelerate in response to a force. Because Newton tells you forces cause acceleration, but their acceleration is not the same on different objects. Certain objects resisted more than others, they are said to have a bigger mass. And we can be precise about how much bigger by saying if the acceleration of a body to a given force is 10 times that of a 1 kilogram mass, then its mass is then 1/10 of 1 kilogram. This is how masses can be tabulated using a spring. So imagine then, from now on, we can find the mass of any object, right? We know now with the same spring, by this comparison, we'll find. So all objects now can be attributed a mass. Then we may, from this equation, say a certain force is acting in a given situation by multiplying the m times the a. But then here is what we actually do. Now we go back to the spring. We go back to the spring and we want to learn something about the spring. We want to know how much force it exerts when I pull it by a certain amount. Now I can measure that because I pull it by 1 centimeter and I find the acceleration it exerts on a known mass, that m times a is the force the spring is exerting. Then I pull it by 1.1 centimeter and I find ma. I find 1.2, I find ma. I draw a graph here of the amount by which I pull the spring versus the force it exerts. And it will typically look like this, and the formula we say is F equals minus kx, where k is called the force constant. You got to understand what the minus sign is doing here. This is the force exerted by the spring on the mass. It says if you pull it to the right, so that x is positive, the spring will exert a force which is in the negative direction. That's why you have a minus sign. And then all springs will do something like this. Further out, they can do various things. The force may taper off, force may not be given by a straight line, but for modest deformations, every spring will have a linear regime in which the force is linearly proportional to the stretching. It also tells you that if you compress the spring, compress it means x is measured from this position where the spring is neither compressed nor expanded. So x is not really the coordinate of the end point. You got to understand that. Springs have a natural length. So x is measured from that length. If it's positive, it means you stretched it. If it's negative, it means compressed. And this equation is telling you if you compress it, namely if x is negative, F will be then positive because it's pushing you outwards. Therefore, what we have done now is we can take all kinds of springs and we can calibrate the force they will exert under various conditions. Namely, if you pull it by so much, that's the force it will exert. So I want you to think for a second about two equations. One equation says F equals ma. Other equation says F equals minus kx. So what's going on? I mean, is one of them Newton's law? Then what's the other one? Maybe F equals minus kx should be called Newton's law. Why is F equals ma called Newton's law? Then what's the meaning of this expression? What's the difference between saying F is minus kx and saying F equals ma? They're saying very different things. Yep.
F equals ma is a universal law.
Right. Let me repeat. F equals ma is universally true, independent of the nature of the force acting on a body. And then?
And F equals negative kx is only describing how a spring works.
Very good. That's the whole point. So the cycle of Newtonian dynamics has two parts. First one says, if you knew the force acting on any body, without going into what caused the force, then you may set that force equal to the mass times acceleration of the body. We think of force as the cause and A as the result or the effect. Force causes acceleration, and this is a precise statement. There, Newton doesn't tell you what forces are going to be acting on a body in a given situation. If you leave the body alone, maybe there's no force acting on it. If you connect the body to a spring, which is neither compressed nor extended, there's no force acting on it. If you pull the spring, there is a force acting on it. Newton is not going to come and tell you what force the spring will exert when it's pulled by some amount. That is another part of your assignment. So the physicist has to constantly find out what forces act on bodies. That's a separate exercise. In every context in which I place a body, I'll have to know what are the forces acting on it. I've got to find them by experimenting, by putting other bodies and seeing how they react, and then finding out that's the force that acts on a body when it's placed in this or that situation. Once you got that, then you come back. So in the case of a spring, this is the law that you will deduce. If it's something else, you will have to deduce another law. For example, we know that if a body is near the surface of the earth, the force of gravity and that object seems to be m times g, where g is 9.8. That's something you find out by experiment. So every time you're finding out a different force that's acting on a body with different origin. One says, leave any body near the earth, it feels a force. I know this is the right answer, because if I now find the acceleration, I find it's mg divided by m, and I get minus g as the answer for all bodies. By the way, that's a very remarkable property of the gravitational force, the cancellation of the two m's. If you look at the electrical force, the force of, say, the proton and the electron or something, is not proportional to the mass of either object. It's proportional to the electric charge of either object. Therefore, when you divide by the mass to get the acceleration, the response to different bodies is inverse to the mass. But gravity has the remarkable property that the pull of the earth is itself proportional to the inertia of the object. So that when you divide by m, m cancels, and everything falls at the same rate at the surface of the earth. In fact, it's a property of gravitational fields anywhere, even in outer space, where there is some residual field due to all the planets and all the stars in the universe, that the force on a body is proportional to the mass of the body. So when you divide by the mass to get the acceleration, you get the same answer. Everything, gold, silver, diamonds, particles, everything accelerates the same way in a gravitational field due to this remarkable fact. And this was known for a long time, but it took Mr. Einstein to figure out why nature was behaving in that fashion. If I have some time, I'll tell you later. But there are two qualities which happen to be equal. One is inertial mass, which is how much you hate your velocity to change, how hard you resist acceleration. That exists far from planets, far from everything. Other is gravitational mass, which is the measure of how much you're attracted to the earth. There's no reason why these two attributes had to be proportional. But they're proportional and they're equal by choice of units. And you can ask, is it just an accident or is it part of a big picture? It turns out it's part of a big picture. And all of general relativity is based on this one great equivalence of two quantities which have very different attributes. why should the amount by which you're attracted to the Earth be also a measure of how much you hate acceleration? Two different features, right? But they happen to be the same. Anyway, what physicists do is they put bodies in various circumstances and they deduce various forces. This is the force of gravity. This is the force of the spring. Here's another force you might find. You put a chunk of wood on a table and you try to move it at constant speed, then you find that you have to apply minimum force. But you're moving at constant velocity. That means the force you're applying is cancelled by another force, which has got to be the force of friction. So force of friction is yet another force. Then there are other forces, right? You guys know there's the electrical force. If you bring a plus charge near a plus charge, if my body M has a plus charge and another plus charge is there, it'll feel a force due to that. That's not going to be given by Newton. So Newton did not ever tell you what the expression for force is in a given constant. That is a constant study. Coulomb discovered the Coulomb's law, which is the repulsion between charges. And nowadays we know if you go into the neutron or proton, there are quarks. There are forces between the quarks. And you can ask what's the force that this quark will exert on that quark at a certain separation. That's obviously not known to Newton. So remember, Newton said F equals ma, but didn't tell you what value F has in a given contest. He just said whenever there's an acceleration, it's going to be due to some forces, and it's your job to find what the forces are. And to find the force, what you will do is, suppose somebody says, hey, I've got a new force. Every time I go near the podium, I find I'm drawn to it. Okay, that's the new force. You know, word gets around, and we want to measure the force. So what do? I stand near this podium. I'm drawn to it. I cannot stop. So I tie a spring to my back, and I anchor it to the wall, and to see how much the spring stretches before the two forces balance. Then I know that the kx is equal to the force this is exerting at this separation. I move a little closer, then I find the stretching is a different number. Maybe the force is getting stronger. That's how, by either balancing the unknown force with the known force, or by simply measuring my acceleration as I fall towards this podium and multiplying by mass, you can find the force it exerts on me. So it's not a cyclical and useless definition. It's a very interesting interplay, and that's the foundation of all of mechanics. So we are constantly looking for values of F, and we're constantly looking for responses of bodies to a known force. So here's a simple example of a complete Newtonian problem. A mass is attached to a spring. It is pulled by a certain amount, x, and is released. What is it going to do? You go to Newton. Newton says F equals ma. So to make it a useful result in this problem, we know the mass of this guy. We did the comparison with the elephant or something. A is the second derivative of x. And for this problem, when F is due to a spring, we know the force is that by studying the spring, and suddenly you have a mathematically complete problem. Mathematically complete problem is that you can find the function x of t by saying that the second derivative of the function is equal to minus k over m times the function. Then you go to the math department and say, please tell me what's the answer to this equation. We don't have to worry about how you solve it, but it's a problem in mathematics, and the answer will be, surprise, it's going to be oscillating back and forth, and that'll come out of the wash. But this is how you formulate problems. You can formulate another problem. Later on, we know about gravity, right? Newton finds out there's a force of gravity acting on everything. Here's the sun. Here's your planet. And at this instant, the planet may be moving at that speed. Then the acceleration of the planet is the force of gravity between the planet and the sun, which Newton will tell you is directed towards the sun, and it depends on how far you are. So depending on how far the planet is from the sun and where it's located, you will get the left-hand side. That's another law. That's a law of universal gravitation. Then again, you will find the evolution of the planetary motion, because the rate of change of a position is connected to the position. Then you again go to the math guys and say, what's the answer to that? And they tell you the answer, which will be some elliptical motion. Okay. By the way, Mr. Newton did not have math guys he could go to. So not only did he formulate laws of gravitation, he also invented calculus. Then he also learned how to solve the differential equation for calculus. So he probably felt that nobody around was doing any work, because all the thing was given to this one person. It's really amazing that what Newton did in the case of gravity was to find the expression for this. And a few months or a few years earlier, he had also gotten this law. By putting the two together, out comes the elliptical motion of the planets. Okay, so we'll come back to that, but you have to understand the structure of Newtonian mechanics. Or generally, any mechanics will require knowledge of the force. Now, I'm going to add one more amendment. You don't have to write in your notebook, but you got to remember, maybe you'll put a little T and circle it. Let me write it here. Ft means the total force on a body. If there are many forces acting on a body, the acceleration is controlled by the sum. If I'm now working in one dimension, it's obvious because I'm not using any vectors, then you may have forces to the right, forces to the left, pushing, pulling. You add them all up algebraically, keeping track of their sign, and that's the total force. That's connected to mass times acceleration. Okay, now I'll give you the third law. The third law says that if there are two bodies, then called 1 and 2, force of 1 on 2 is minus the force of second on the first one. This is the thing about action and reaction. And all the laws that anybody knows have this property. So what does it require to be a successful mechanic, to do all the mechanics problems? You got to be good at writing down the forces acting on a body. That's what it's all going to boil down to. So here's my advice to you. Do not forget the existing forces and do not make up your own forces. I've seen both happen. And right now, at this point in our course, whenever you have a problem where there is some body and someone says, write all the forces on it, what you have to do is very simple. Every force, with one exception, can be seen as a force due to direct contact with the body. Either a rope is pulling it, rope is pushing it, you're pushing it, you're pulling it. That's a contact on the body. If nothing is touching the body, there are no forces on it, with one exception, which is, of course, gravity. Gravity is one force that acts on a body without the source of the force actually touching it. That's it. Do not draw any more forces. And people do draw other forces. When a body is going around a circle, they say there's some centrifugal force acting. There is no such thing. So be careful. Whenever there is a force, it can be traced back to a tangible material cause, which is all the time a force of contact, with the exception of gravity. Okay, so with that, if you write the right forces, you will be just fine. You'll be able to solve all the problems we have in mechanics. So I'm going to now start doing simple problems in mechanics. They'll start out simple, and as usual, they will get progressively more difficult. Okay, so let's start with our first triumph will be motion in 1D. Here is some object. It's 5 kilograms, and I applied 10 newtons. And someone says, what's the acceleration? And everyone knows it is 10 over 5 equals 2. But now we know how you got all the numbers that go into the very question. How do we know 10 newtons is acting? Now, I think you people know how we can say that with confidence. How do we know the mass of this is 5 kilograms? You know how you got that from an earlier experiment. So now we know how the numbers come in. The algebra is, of course, very trivial here. Then the next problem is a little more interesting. So here I got 3 kilograms, and I got 2 kilograms, and I'm pushing with 10 newtons, and I want to know what happens. So one way is to just use your common sense and realize that if you push it this way, these two guys are going to move together, and know intuitively that if they move together, they will behave like an object of mass 5, and the acceleration will again be 2. But there's another way to do this, and I'm going to give you now the simplest example of the other way, which is to draw free body diagrams. By the way, when I say there's 10 newtons acting this way, you might say, what about gravity? What about the table? So imagine that this is in outer space where there is no gravity for now. So the motion is just along the x-axis. So the free body diagram, it says you can pick any one body that you like, and apply F equal to ma to it, provided you identify all the forces acting on that body. So we'll first pick the body with mass 3. Here's the body of mass 3. What are the forces on it? This is certainly acting on it. Then you have to ask what other force is acting. So here is where you have to think. Yep. Anybody want to guess from the last row what force? Yes?
The reactive force of 2 on 3.
Right. So let's give it a name, right? So let's point it that way and call it F2 on 3. That's the end of this guy. Then let's look at the other fellow. Maybe you should complete the force acting on this one. Can you tell me what it is? Same person from the last row.
Got the force of 3 acting on 2 in that one.
And how big is that?
Same as F2, 3.
Right. So I don't want to give it too many different names, right? Because F23 and F32 are equal and opposite. I'm already showing F23 acting to the left. So let me give it some other name like F. Then you agree this would be the same F but pointing that way. And here is a mistake some people make. They add to that the 10 newtons. It's the 10 newtons acting on it because I know the 10 newton is pushing me and I'm going to feel it even if I'm here. That would be a mistake. That's an example of adding a force that you really shouldn't be adding. The only force acting on this guy is this little f. And that's in turn because this guy is being pushed by the 10 newton, but that's not your problem. Your problem is to only look at the forces of contact on you, and that is just this f. Then we do F equals ma for these two guys. For this guy, F equals ma would be 10 minus f is 3 times a. The other one, it will be F equals 2a. And notice I'm using the same acceleration for both. I know that if the second mass moved faster than the first one, then the picture is completely wrong. And if it moves slower than the first one, it means it's rammed into this one. That also cannot happen. So they're moving with the same acceleration. So there's only one unknown a. So once you got this, you realize what you got to do, right? This equation is begging you to be added to this equation. Right? You got a plus f and a minus f, so you got to do what you got to do. You add the two, you get 10 equals 5a, and you get a equals 2. Once you got a equals 2, you can go back and realize here that f is equal to 4. And so you got really 4 newtons. Now we know the full story. 4 newtons acting on 2 kilograms gives you an acceleration of 2. On this guy, I have 10 from the left, and I have 10 acting this way, 4 acting that way. That is 6 newtons divided by 3 kilograms is also acceleration of 2. This is a simple example of free body diagrams. Very simple. If you can do this, you can do most of the problems you will run into. Just don't add stuff that's not there. That's all you have to be careful about. And the stuff that people tend to add sometimes is to keep drawing the 10 newton as acting on that. Okay, now here's another variation. The variation looks like this. I got 3 kilograms and I have a rope and I got 2 kilograms and I pull this guy with 10 newtons. What's going to happen? Again, your common sense tells you, look, you're pulling something whose effective mass seems to be 5. The answer is 2. But let's get that systematically by using free body diagrams. Now there are really 3 bodies here, block 1, block 2, and the rope connecting them. Now, in all these examples, this rope is assumed to be massless. Now, we know there is no thing called a massless rope, but most ropes have a mass which may be negligible compared to the 2 blocks you're pulling. So we'll take the idealized limit where the mass of the rope is 0. So here is the deal. 3 kilogram is being pulled by the rope on the right with a force that I'm going to call T, which stands for tension. the rope is being pulled backwards by this guy with T. And what is the force on the other side? What should that be? Who said T? And why is it definitely T and not something else? What would happen if it's something else?
If it was greater than the rope would snap. Well, if it was greater,
It won't snap, but something else will be a problem. Yes? Not only faster, what will be its acceleration? If the two forces don't cancel, you have a net force. What are you going to divide by to get the acceleration? 0, right? So massless body cannot have a net force on it because the acceleration of the rope cannot be infinite. In fact, it has to be some finite number, which is the acceleration of either of these two guys. So massless bodies will always have, like a massless rope, equal and opposite forces on the two ends. And that is called the tension on the rope. So when you say the rope is under tension, being pulled from both sides by a certain force. The tension is not 0 just because this T and that T cancel. It's true the net force is 0, but doesn't mean you can ignore it, right? Suppose you're being pulled by my favorite animals, the elephants, from both sides by equal force. You don't find any consolation in the fact that these forces add up to 0, right? You feel the pain. That pain is what we, this gentleman doesn't agree. One of you guys nodding your head. You feel the pain, you agree? Okay. That force is called the tension. So you, whenever you're asked in a problem, what's the tension on the rope, you're looking for that equal and opposite forces acting at two ends of the rope. So we don't know what it is. We'll give it a name. But by linking that T to that T, you can also figure out the same T must be exerted on this one by Newton's third law. Because if this block is the only one that could be pulling this rope with T, therefore the rope should be pulling the block with T in the other direction, then I got 10 newtons here. Now you can do F equals ma for the 3 different objects. There's nothing to do here because the forces are 0, the mass is 0, it doesn't tell you anything. The first one tells you T equals 3a. The other one tells you 10 minus T equals 2a. Now again, we know what to do. We add these numbers and we get 10 equals 5a. Therefore, we find a equals 2. Once you find a equals 2, you find T equal to 6. So tension on the rope is 6 newtons. Now this is very important because when you buy a rope, they'll tell you how much tension it can take before it will snap. And if your plan is to accelerate a 3 kilogram mass with an acceleration of 2 meters per second, you better have a rope that can furnish that force and which can take the tension of 6 newtons. All right. Now for the, whoa. Okay, I'm going to give the last class of problem, which is pretty interesting, which is what happens to you when you're in an elevator. So here is a weighing machine, and that's you standing on the elevator. And we're going to ask, what's the needle showing at different times? First, take the case in the elevator is on the ground floor of some building and completely at rest. Then let's look at the spring. The spring is getting squashed because you're pushing down and the floor is pushing up. You're pushing down with the weight mg, and the floor has got to be pushing up with weight mg because the spring is not going anywhere. So the spring is being pushed by mg here and mg here. Therefore, it will compress by an amount x, which is equal to mg divided by the force constant of the spring. By the way, that's a subtle thing people may not have realized. Even in the case of this spring, when you pull it, if you pull it to the right by some force, remember the wall is pulling to the left with the same force. So springs are always pushed or pulled on either side with the same force. We focus on one because we are paying for it, but the wall is doing the opposite. We don't pay any attention to that. But you cannot have a spring pulled only at one side because then it will then accelerate with infinite acceleration in that direction. So this spring is getting squashed on either side, and it will squash by a certain amount x that depends on your mass, and that x will be turned into a motion of a needle, and that will read your mass. Now what happens if the elevator is accelerating upwards with an acceleration a? That's the question. Now the way I analyze it is I say, if I look at me and I write the forces on me, that is mg acting down, let me use W as the symbol to represent the force exerted by the spring. W minus mg is ma. That is F equals ma. When I was not accelerating and everything was at rest, ma was 0, W was mg, and W was the reading on the needle. But if I'm accelerating, the force exerted by the spring, and therefore the needle, the weighing machine reads, is m times g plus a. That means when you're accelerating upwards, as the elevator picks up speed, the reading on the spring will be more and you will feel heavy. You feel heavy and it reads more because the poor spring not only has to support you from falling through the floor, but also accelerate you counter to what gravity wants to do. That's why it is g plus a. So you picked up some speed, then you're coasting along at a steady speed, then a drops out and you weigh your normal self. As you come to the top of the building, the elevator has to decelerate so that it loses its positive velocity and comes to rest. So a will be negative and W in fact will be less than mg. So you will feel weightless for a short time, or you will feel your weight is little, then you come to rest. Then the opposite happens on the way down. Let me just briefly look at the ride on the way down. As you start on the top and go down, your acceleration is negative. Remember, you've got to keep track of the sign of acceleration. So if you're picking up speed towards the ground, a is negative, so it will be g plus a, but a is a negative number. So let me write it as g minus the absolute value of a. And you can see that if a was equal to g, your downward acceleration is that of gravity, namely the cable has snapped in the elevator, then you don't feel any weight. You don't feel any weight because your weight is the opposition you get to falling through the floor, but if the floor is giving way and you're just falling freely, you feel weightless. So it's wrong to think that you feel weightless because you've escaped the pull of gravity. We all know that when you're falling elevator, you've definitely not escaped the pull of gravity. It's going to catch up with you in a few seconds. Likewise, when you're in outer space, when you're orbiting the Earth, people are always floating around in these space stations. They have not escaped the pull of gravity either. They have just stopped fighting it. If you escape the pull of gravity, your spaceship will be off, won't be orbiting the Earth. So anyway, I will return to this next time. So do your problems. Now there's quite a few problems. You should start them right away.